Hello folks, my name is Lindsay Rusnak and I am a science teacher at Lake Braddock, and I'm here today to talk to you about the chemistry of glazing. A little bit about my experiences combining my interest in art and science. I took a ceramics class in high school and followed it up with advanced ceramics in college. I am currently a student at the Workhouse Art Center in Lorton, Virginia, where I take ceramics classes. And I specifically took a Chemistry of Glazing course last summer, so I thought I'd share some of the things that I'd learned and researched with you. So first, let's start with some basics. What is a glaze? So glaze is basically a glass coating added to a ceramics piece for waterproofing, coloring, or decorating that piece of pottery. And it's made of three main components. We call those silicas, aluminas, and fluxes. So silica is a glass former. It's a combination of silicon and oxygen. Our fluxes are things that can help melt glass because silica melts at a very high temperature. And flux is Latin for the word flow. So it's helping that glass flow over the piece. And then alumina is our aluminum and oxygen combination, and it helps stabilize the glass. So the first component of our glasses are our glass formers. So that's our boron and our silicon. So silicon dioxide and boron trioxide are the main components of glass. And they can be combined and used in different combinations and actually form what is called a borosilicate glass. And that's what Pyrex is made of. So Pyrex has an advantage because it doesn't shatter with thermal shock. So when glass is made with just silicon dioxide, if you heat it and then cool it, it will break. So borosilicate glasses like Pyrex are much more resistant to thermal shock. And they do need to be in the right combination in order to get that maximum benefit. So that's the main component of our glaze, is that glass former, a combination of silica and boron. We also have our fluxes. So our fluxes are made of a combination of oxides. So our alkali metal oxides and our alkaline earth metal oxides are our glass melters. So they allow those crushed gas particles in the glaze to melt at kiln temperatures. So a kiln can be set to about 550 degrees Celsius for, a standard cone 6 melt, whereas silica melts at 2000 degrees Celsius. So to put that in Fahrenheit, since some of us are a little more familiar with Fahrenheit, the glass can melt at 1020 degrees Fahrenheit instead of 3600 degrees Fahrenheit. So our alkali metal oxides, alkaline earth metal oxides are put in order to help melt that glass. And for anyone who is a chemist person, we have our alkali metal, and there would be 2 alkali metals for every oxygen, whereas our alkaline earth would have a ratio of 1 alkaline earth metal to 1 oxygen. And that does play a role in its impact. The alkali earth metals and alkali metal oxides and alkali earth metal fluxes do behave in slightly different ways. So depending on what a glaze is going for, in texture and melt temperature and overall behavior, we can use different pieces of that. And finally, our glass stabilizer has some aluminum in it, our aluminum oxide. So that's helpful, especially in pieces with a lot of curvature to them, and keeping that glass stable during firing and cooling. And then the exciting piece that people tend to care about is the transition metals. And those are what makes a glaze unique. So a lot of transition metals come into play and are the colorants. This is just a sampling of them. There are more that could be used, but we'll talk a little bit about why not all of them are options for us as we move forward. So glass can be a lot of different colors depending on which of these transition metals are added to a piece. So this is just a graphic I found of some different color combinations. And you can see things how iron on its own gives us this emerald green color, but when mixed with sulfur, we get more of an iron brown rusty color. Chromium in the scenario that was seen here, we give green, but chromium can also be red if put in combination with other elements and heated to the right conditions. Manganese makes this really cool purple, and I want to highlight it. If you have ever been out to Seattle, Seattle was actually built at a lower elevation, and at one point there was a fire that burned things down, and they literally just built the new city on top of it. There's really actually some fascinating history there if you ever get to go to Seattle. But there are underground tunnels that were once lit by glass made with manganese. And over time in the sun, the manganese has turned this purple color. So if you're ever up in Seattle, you will see little checks of purple glass in the sidewalks. A lot of them have been replaced due to deterioration and not wanting people to be hurt if they trip on it. But if you've ever seen the purple sidewalks or take a look at them, I just think that's kind of a cool story of, history of a town. But the purple sidewalks of Seattle are due to manganese. So these different colors here can be used. There are some clearly that we're not going to see as often. Here's some uranium in the middle, this green color. I'll talk a little bit more about uranium on a future slide and why we don't use it so much anymore. And just to give you an idea of the variation of glazes, depending on the temperature something's fired at, the other elements in combination, the amount of colorant you put in. Something like iron can run a gamut from gray to green to orange to brown. If you've ever used oxides to stain, I know I've used rutile, a more yellowy iron form, brownish red iron, red oxide, and black oxide. All of those just have different formulations of iron put in different conditions. So there is a lot of flexibility, but that also means that a lot of ceramics has to be really carefully tested to make sure that you're going to get the look that you want on a finished piece. Something like copper. Copper is very versatile. It can be used as a colorant and give you a really bright aqua color like you can see in the mug on the left. The bowl on top, you see that green like the Statue of Liberty and red like a copper penny. That has to do with the atmosphere in the kiln when that piece was fired, and I'll talk a little bit more about that in a future slide. And then on the far right is a raku piece with some copper in it, and I'll talk a bit more about raku. But with our transition metals, because transition metals can exist in different forms, they're going to react with the clay body, the atmosphere in the kiln, and the other components in the glaze and give you really different results depending on what they are mixed with. And here's just a few other examples of how transition metals can give us different colors depending on what they're mixed with. So on the far left, I have some bowls with cobalt. Cobalt is that very distinctive royal blue glaze. It's very consistent. It's been used commonly throughout time to give us that nice, beautiful blue color. But cobalt can also give us a purple color when used in very small amounts. When mixed with other things, you can see that the blue has been dulled here in this piece. And then something like chromium. Chromium can give us anything from this cranberry raspberry color to these jade green colors depending on what things are mixed with. And here, these are just some sample recipes of what's in a glaze. So basically we take materials that are mined from the earth, clay that has been deposited from erosion over time in different areas, and mixed together to give us a glaze that we can rely on. If you are a ceramics student, you may notice that you can't always get a red or an orange that's in the color that you're looking for. A lot of the reds that I use tend to be more brown and irony, as in filled with iron. And the reason is that a lot of red glazes and a consistent red glaze are made with things that are hazardous to our health. So things like lead and uranium are watched by the FDA, and we are not allowed to have them. So lead makes for a good red glaze, and we can't use it anymore. So really old china can have traces of lead, and especially over time, that lead can leach out from the glaze and could injure somebody. And lead to lasting consequences. If you've never heard of Fiesta Ware, really popular commercial line available at a lot of places in a whole range of colors. But back in the day, their beautiful orange glaze had uranium in it. So this photo is just some Fiesta Ware with a Geiger counter on it, and it is in fact radioactive. So this is not going to be used in making a bomb. If you had some of this vintage Fiesta Ware, it's not so much to be like a huge concern, but clearly we aren't going to have uranium-laced pieces commercially available anymore. So you can find lots of pictures of orange Fiesta Ware on the internet that shows that it does have that trace amount of radiation. So some of the alternatives that we have today for red glazes use things like chromium, and they do something called encapsulation. So chromium's still not that good for you, but they basically encase it in a crystal of something else that is safe for you, and that traps the chromium so it can't leach out. But if you've ever felt like I can't get quite the shade I want in a piece I'm going for, a lot of times it's because the transition metals that we have access to just don't give you what you want. I know a frequent question that I hear is, how do we get different colors with the same metals? How come a glaze looks so weird before I put it on my piece and I get such a different color when it's transformed in the kiln, when it goes through that heating and cooling process? We undergo a process called vitrifaction. So basically all of these atoms and elements are breaking and reforming in the heat of the kiln. And so depending on what is in the glaze, what is in the clay body, what is in the atmosphere of the kiln, we get new combinations of the atoms. So here's one example. Cobalt we typically think of as, like I said earlier, that royal blue, deep saturated blue color. And when it's surrounded by 4 oxygens in what we call a tetrahedral arrangement, we see blue cobalt to our eyes. Pink cobalt can also exist in what we call an octahedral form. So remember at the very beginning of the presentation, I mentioned that the alumina and the silica all have oxygen atoms trapped within those raw ingredients. So depending on the heat and the movement of electrons, cobalt is going to bind with different types of atoms, and it's going to bond with oxygen in different arrangements. So that tetrahedral blue cobalt is what we most commonly see. At the bottom, I've put a link to an article that talks a lot about the electron movement and the arrangement of atoms and gets really deep into chemistry. So check out that link if you're interested later on. I thought it was kind of a cool resource, but I didn't want to make your eyes glaze over. So I know I've mentioned the atmosphere inside the kiln a lot, and I do want to talk a little bit more about that. So when a kiln is being fired, we have to look at the balance of oxygen within the kiln. So at school, most people who have a private kiln, they're firing an electric kiln. So an electric kiln tends to be what we call a neutral atmosphere, or tends to be an oxidative atmosphere. And it will burn in what we call oxidation. Gas-fired kilns are a little trickier in that you have to kind of vent and allow different amounts of oxygen in order to get the result that you want. So when a kiln is fired, the heat and the atmosphere around it is going to impact how those electrons move and what molecules are going to form as all those molten things cool down. So an oxidation kiln is what we most typically see as the result of an electric kiln firing. And this is where there's plenty of oxygen in the kiln when burning fuel. So well ventilated, but also with an electric kiln, that heat source is just not gas and is not coming from the combustion of a gas. And if you remember, combustion, burning fuel, is always going to make oxygen as a product. So a reduction kiln is where oxygen is being limited. And in the burning of that fuel, because oxygen is limited, instead carbon monoxide is going to be made. So soot from a gas can also add electrons and bind to those liquid glazes as they are being fired. And that will add electrons, and that will make different colored compounds. So on the right, we see a copper glaze. So copper was the colorant, and depending on how it was fired, you either get that Panama red, that maroon burgundy color, but if it's fired in oxidation, you get Statue of Liberty green. So if you are going for the red, you'd have to put it in a kiln, and it would probably have to be a gas kiln, and you'd have to really deprive the kiln of oxygen so that you would be favoring the carbon monoxide. I've loaded gas kilns in my studies, and it's very critical in how closely you place the pieces together, where you place them in the kiln, how close they are to any sort of vent that would allow the exchange of oxygen into that kiln. So, artists know their kilns and get very experienced in trying to get the results they want. And you can also intentionally do those pieces where maybe one side is more oxidized and one side is more reduced, depending on airflow inside that kiln. So there really is a lot of artistry in this chemistry. So what other factors do we have to consider? We have to consider how hot we're making the kiln. So you've probably heard of, right, cone 6, cone 10, cone 05. Those are different temperatures that the kiln is going to reach. So when you're making a glaze, you have to look at the balance between the glass formers, the glass melters, and the glass stabilizers, and make sure that they are going to expand and contract at about the same rate as your clay body. So you really can't just go and dig clay out of your backyard and necessarily make a piece that will end up being functional at the end of the day, only because you don't know exactly what's in that clay and what temperature you need to fire it at to make it stable. So when making a glaze, we also have to consider, are they a mid-fire, are they a high-fire glaze, and working with that clay body. In the heat of the kiln, every piece is going to expand and contract. So the clay and the glaze need to expand and contract at similar temperatures and bond together. So if the clay is shrinking too quickly, glaze is going to peel off. If the glaze shrinks too quickly as it cools, you'll get crazing. And crazing is that crackling effect. So often it's an artistic choice, but it's often an unintended consequence with that wrong mix of raw materials. So just a little image of looking at the peeling versus the crazing, and really trying to get the glass bonded to the clay body to make a stable piece that will last for years. And also if you're trying to make it food safe, if you want it to be a serving bowl, something that has a lot of crazing or crackling or peeling could lead to glass chips, which would be undesirable as a piece that serves food. Layering glazes. So you may have made test tiles in your past. You may have experimented with mixing two different glazes together. And a lot of times when you're layering a glaze, you get some unintended consequences. So a glaze that's typically stable may form an unexpected chemical composition when it's heated and is able to mix with other components in the clay body or in another glaze, giving some different results. Some elements can interact with others and change color. For example, if you are someone who uses underglazes, you typically put an overglaze that is zinc free. Zinc tends to really change the intended color of an underglaze. It'll change purples to more blue, but especially with an underglaze, when you're hoping to have that integrity of color in the final piece, having something like zinc could impact the final color you're getting. You also have to be careful that when you mix two glazes together, that now you have a different combination of fluxes, which means things are going to melt at different rates. So it's possible to have a eutectic layering of glaze. So basically a synergistic effect where the overall melting point is lower than any individual glass piece in your glaze. So this is just a picture of a layering of 3 different glazes. And as it melted, the glaze on top melted at a lower temperature and really ran on the piece. So as an artistic decision, it's beautiful and can be intentional. And then sometimes you end up having to chisel your piece off of a kiln because you had a little too much running. So that's why it's always good to, make a test tile, especially with new glazes, to see how they work in combination. The balance of materials plays a big difference in the stability and appearance of a glaze. So the ratio of glass formers to glass stabilizers to fluxes, the temperature at which a glaze is fired can be a big difference between a safe glaze and an unstable glaze. Matte glazes are not always as common as we would like. A high gloss we tend to think of with that glassy covering of a glaze, but matte glazes are obviously desired for their own artistic choices. What you have to be careful of is that a matte glaze is sometimes not the most stable. And a lot of times there's a lot of online resources where artists share recipes for glazes. And they'll say, hey, look, I made a really cool matte glaze. It's super stable. It's really predictable. And if you accidentally overfire it, it comes out of the kiln and it's super shiny. And if that's the case, that really means that the balance of glass stabilizer and glass former was not correct. And you haven't, in fact, made a stable glaze. So a matte glaze that is reliable and food safe can be difficult to find because of that chemistry involved. So this chart here looks pretty complicated. You can see the matte portion here where there's just a little more aluminum in that ratio compared to the silica. And all those things are taken into consideration when an artist is developing a new glaze, especially if they're looking for a matte glaze, to make sure that it will be stable enough. This is a triaxial blend. So basically, when we are pulling the raw materials for our glaze, they're being mined from the earth. And so we need a blend of these different clay and glass components. And this is just a very day one chemistry of glazing class that we have just a different mix in different proportions of 3 main components that together form a glass. And what you see in different pieces of this triangle is that some of them look nice and glaze-like, and then some of them are just lumps that they might not even necessarily melt. If they do melt, they don't necessarily fuse to the piece. I had an instructor who brought one of these into class, and half of the pieces were just hot glued into the cups because they didn't fuse it all to the clay body underneath and would just fall off. So you can see where you got some melting, but not necessarily a fully formed glaze. You can see that this glaze has some pinholing, so maybe not necessarily the look you're going for, but other combinations will give a better piece. So this is a pretty basic how do you blend a glaze introduction. But it's really common to see taking some of those raw components from the mines, mixing them together, and just seeing what melts at the temperature in the kiln you have. Some of the things to consider, because of those raw materials are coming from mines, if the mine opens a new vein, or if they dig far enough, there could be a change in composition. So an example would be our very own Washington Monument in DC. All of the materials for the Washington Monument came from the same quarry. The difference is that the Washington Monument started to be built, and then they ran out of money, and it sat there for a very long time not being finished. Eventually, funds were raised to finish the monument, but there is that noticeable color difference. And that's because the raw materials from the mine changed very slightly in composition. So the mine, they kept digging through the quarry, and so that material now has a slightly different color to it. So in chemistry, in these mines, when people are mixing glazes and buying powders, they are buying natural materials that are going to vary. So there's a clay called like Old Kentucky 17, and as it turns out, that mine shut down, and so now like it's Old Kentucky 21 because it's from a different piece of the mine. And so for a lot of artists who make their own glazes, when the mine runs out, they have to redesign all their recipes for their glazes because the materials aren't the same anymore. And then on the right, this is just a picture of some different colored frits. Those are lab-made pieces of glass. And so they're more expensive, but they are very reliable. You know exactly what's in them, and you can predict exactly what's going to happen with them. So using a frit might make a glaze more reliable. It will also make it more expensive. And then hopefully I haven't bored you too much, but it's just everything I've talked about too is just a start. So I just want to talk about some other firing techniques you may have heard of and just show you the wide variety of things that you can do with your pieces just by knowing a little bit about art and chemistry. So raku is a really popular firing technique, especially when the weather's nice. And there's the Eastern Japanese style and the Western style. I've done the Western style firing before, and basically you heat your piece to red hot and you very quickly pull it out of its kiln and you put it into a container with like newspaper or wood chips, but something that burns very easily and pulls the oxygen out of the atmosphere. So raku is in that reduction state with a lot of carbon monoxide, a lot of carbon soot, and oxygen is pulled out from the clay body itself. Carbon from the atmosphere of the kiln is deposited on the piece. And so raku has this black coloring wherever it is unglazed in the final clay body. And because you're taking raku from a red hot kiln and putting it into another container, that is going to make the exterior cool very quickly. And so when we talk about that crazing and crackling, that is an intentional effect of a lot of the raku glazes. So that's how we can get that crackle effect. So raku, very lovely technique. It's very versatile depending on the type of glaze you're using. You can do so many things with it. You can get that really shiny metallic copper color depending on the conditions and the type of glaze you put on. A salt firing kiln is also a really common technique. So in a salt fire, it's typically with a gas kiln, and you set the kiln at a really high temperature and you literally just pour in table salt. You can also soda fire with some other materials. So when the salt is put into the kiln, it vaporizes, it turns into a gas, and it combines with the clay body, forming this hard, glossy sodium silicate glaze. So you can actually put in bisque-fired pieces into a salt kiln, and they will end up with shine and texture, even if there's no other glaze on it. And so salt kilns are really popular for adding some interesting texture, and also for, working with glaze in a slightly different way. So the piece on top, you can see a lot of texture. The piece on bottom, a salt-fired kiln, playing with slips, and looking at that salt firing result. A lot of different things that can happen with it. It usually gives you a more rustic quality in your final pieces. And crystalline glazes, these are really popular. I know we have an artist at the workhouse that does a crystalline glaze class. It's intense. Most of their pieces fail, but it's a really cool thing to see a finished piece when it works. So crystalline glazing is a really unique process in that you put the glaze on very thickly. The base components are a little different than in a traditional glaze, and they're heated and they're cooled very slowly in order for those crystals to grow. If you think of the cooling of lava, obsidian cools very quickly, so there's no time for a crystal to form. Whereas granite is also cooled lava, but it's cooled much more slowly and you get that crystal formation. So it's a similar concept here, that a crystalline fired kiln is put at its high temperature to melt everything, and these seed crystals start to form, and then it's cooled down and kept at this special cooling temperature to encourage crystal growth, and then it's cooled fully and the piece can come out of the kiln. So crystalline glazes usually have a slightly different chemical composition with a lot of zinc, titanium, or lithium to be those crystal seeds. But it's a really popular technique. It's really beautiful. There's so many options. So I just hope that you enjoyed learning a little bit about the chemistry of glazing. It really is art meets science. And thank you for joining me today. I have just links here. None of those pieces were my own. A lot of those graphics also came, from the internet. So I wanted to give any artist, their credit because clearly, we value their work. So thank you so much for joining me today. Have a great day.